Welcome to our channel. Let's begin the journey.
Welcome to this explainer. Okay, today we are unpacking the absolutely incredible, highly dramatic physics of nuclear reactors. We're going to explore what is often called the fire of the atom. Now, this isn't just about those giant concrete cooling towers or massive power grids. It's really about a fascinating microscopic dance of physics that happens in literal fractions of a millisecond. We're going to break down exactly how a single invisible event cascades into a massive, self-sustaining system of just phenomenal power. So here's our game plan for today. 1. The spark of fission. 2. The multiplication factor. 3. The neutron life cycle. 4. The 4-factor formula. 5. The 6-factor formula. And finally 6. Controlling the chain reaction. All right, let's jump straight into part 1, the spark of fission. Before we can even think about building a massive reactor, we have to start at the very beginning. We have to break a single nucleus. And at the heart of our whole story is nuclear fission. Imagine a heavy nucleus, right? Something like uranium-235. It's held together by strong nuclear forces, which act basically like the glue binding its protons and neutrons. But this heavy nucleus is already teetering right on the edge of instability because of the sheer repulsive force of all those positively charged protons just packed in there together. Now, when this nucleus absorbs a slow-moving neutron, it gets intensely excited. It starts to wobble, it deforms, and eventually, snap. The nuclear forces just can't hold it together anymore. It splits into lighter nuclei, it shoots out 2 or 3 brand new neutrons, and crucially, it releases an absolute burst of binding energy. And when I say an absolute burst of energy, I really mean it. A single uranium-235 split yields roughly 200 million electron volts, or MeV. Just to put that into perspective for a second, this single microscopic atomic event vastly, and I mean vastly, outperforms the energy you'd get from any standard chemical reaction, like burning a molecule of coal or natural gas. That one microscopic spark is the exact reason nuclear fission is such a game changer for large-scale power. Let's keep moving. Part 2, the multiplication factor. Well, a single spark doesn't make a roaring fire, right? To transition from the microscale of one atom to the macroscale of an entire reactor core, we desperately need a chain reaction. And the absolutely crucial point in keeping this atomic fire burning without it dying out is the effective multiplication factor. We just call it K. You can kind of think of K as a generational family tree ratio for neutrons. It literally just measures the number of neutrons in a new generation compared to the generation that just came before it. So if K equals exactly 1, the reactor is what we call critical. That means the reaction is self-sustaining, the power is perfectly constant. Now, if K is greater than 1, it's supercritical, meaning the number of fissions in the power level are actually increasing. And if K is less than 1, it's subcritical, meaning our fire is dying out because the fissions are decreasing. Which brings us to part 3, the neutron life cycle. To really wrap our heads around how we achieve that perfectly balanced K equals 1, we have to zoom in again and follow the perilous, action-packed journey of a single neutron inside the reactor core. This whole life cycle happens in a tiny fraction of a second. Okay, step 1 is birth. When a fission event happens, neutrons are born as fast neutrons, just rocketing out at extreme speeds. But here's the catch. Uranium-235 doesn't easily absorb fast neutrons, so we need step 2, slowing down. We also call this thermalization. We use a moderator, which is very often just ordinary water, to literally bounce the neutrons around, bleeding off their kinetic energy until they are slow enough to actually be captured. And finally, we have step 3, diffusion and absorption. Our newly slowed down thermal neutron drifts along until it's either happily absorbed by another fuel atom to trigger a new fission, or it's just lost to other materials. All right, part 4, the 4-factor formula. Now that we know the life story of our little neutrons, let's look at the theoretical math that actually governs their survival. The 4-factor formula calculates K infinity. This is the multiplication factor in a completely theoretical infinite reactor, where neutrons can literally never escape the edges. We figure out the success of our chain reaction by multiplying 4 very distinct probabilities.
Let's rapidly fire through the gauntlet these neutrons have to survive. First up is eta. That's our reproduction factor, simply how many fast neutrons are actually born from the fuel. Next is phi, thermal utilization. Basically, what are the odds our neutron actually hits the fuel, rather than uselessly bouncing into some structural metal? Then we have p, resonance escape. This is the critical probability that a slowing neutron doesn't get prematurely swallowed up by the wrong atoms while it's just trying to hit the right speed. And finally, epsilon. This is a tiny little bonus factor for those super rare fast neutrons that somehow manage to cause a fission before they even slow down.
Notice how we start out with a really wide initial population of fast neutrons. But as we move through the cycle, multiplying by all those survival probabilities we just talked about, P, F, and so on, the population gets relentlessly chipped away. Neutrons get lost to the moderator, or they get swallowed by control materials like boron. The math literally maps out the brutal gauntlet the neutrons have to survive just to ensure that one single neutron remains to split the next atom. Moving right along to part 5, the 6-factor formula. But, we obviously don't build theoretical infinite reactors in the real world. We build physical ones out of concrete and massive steel walls, which brings our theoretical math crashing right back into reality. So here is the fully expanded 6-factor formula. And you'll probably notice it looks exactly like the 4-factor version we just looked at, but with 2 very important additions, right smack in the middle, PT and PF. These 2 new characters are here to account for a super simple physical reality, leakage. Because our core actually has edges, neutrons can just fly out of the system entirely. So PF stands for the fast non-leakage probability. Basically the odds that our high-speed baby neutrons don't immediately escape the boundaries of the reactor. And PT is the thermal non-leakage probability. That's the odds that our fully slowed down neutrons stay inside the core long enough to actually do their job. If we trace this complete equation path, you can follow the entire real-world life cycle. We start with n number of fast neutrons. We multiply by epsilon, subtract the ones that leak out too fast. Then we multiply by p, subtracting the ones swallowed up during the slowdown phase. We subtract the thermal ones that leak out, and multiply by f for the ones that actually hit the fuel. And finally, eta for the new ones that are born. Multiplying our starting neutrons by all 6 of these specific factors yields the exact, precise size of our next generation. And if the math works out perfectly, that new generation is the exact same size as the one we started with. And finally, part 6, controlling the chain reaction. Okay, so we know the variables, but how do we take these abstract equations and actually operate a massive power plant safely? Well, inside that heavily shielded vessel, human operators are constantly manipulating the core's reactivity. See, because materials naturally change as the reactor runs, K naturally wants to drift. To counter this, engineers dynamically alter the math we just learned about. They insert control rods made of materials that just eagerly absorb neutrons, intentionally increasing the loss factors in our formula. By adding this negative reactivity or removing it by pulling the rods back out, operators... At the end of the day, it all comes down to a razor's edge balance. We have the physics, and we have the 6-factor math to ignite the fire of the atom and to harvest an unbelievable 200 million electron volts from just a single microscopic split. But the ultimate question for nuclear engineering is this. As fuels deplete and temperatures shift inside the core, how do we continuously engineer and innovate our reactor designs to ensure we never lose control of that incredible flame? It's just a fascinating testament to human ingenuity. Thank you so much for joining me on this explainer, and I really hope this sparks your curiosity to look even deeper into the physics of our world.
The view from here is breathtaking. Command, we are in position and ready for the next phase. If you liked the video, subscribe and comment the topic you want next. Thanks for watching, and stay unstoppable.